Okay, hello again everyone, and welcome to this video where I'm going to introduce briefly the new version of our dynamic propeller balancing software, version 1.3, that's going to get released soon. And more importantly, I'm going to focus a little bit on filtering and some really cool functionality in terms of advanced filtering with the software, and you'll see how we're going to use that to balance and calibrate our rig. So you can see here I have the software loaded pretty much default, and I have my propeller balancing rig here with a reference blade. And what I also went on ahead and did, I placed a heavy side of a tape, heavy piece of tape there to give me a heavy side. You can also see there's other pieces of tapes here because I had balanced the propeller, so I can show you also what a good balance would look like. The other thing that I want to highlight here, I went ahead and redid some work with our graphics GUI here. Gave it a crosshair. You can actually zoom in and out with the slider, but if you go to it and you hit the shift key and click, you'll see that the cursor turns into a magnifying glass, and using a mouse scroll wheel you can actually scroll and zoom in and out further. And then if you hit Control key, you can actually pan it. So made it very, very interactive. It should make it extremely simple for us to compare graphs and also take measurements from a vibration perspective to see how well your balancing is working. So let's go on ahead and connect the software. Connected to port 5 here, and we'll get a connect message from the Arduino. And then, the way that I proceed with this, with the advanced filtering, is before we do any sort of compensation or worry about inverting X or Y the way we did it in the past with simple low-pass filtering, I actually go on ahead and I will take an initial run to see where I have an imbalance in the propeller. Now for me, 1280 is about 3000 RPMs. And I'm going to take 10 samples, one dummy run. Again, you can determine your RPMs and everything through the ESC controls here. But just with that, I start with 4G and 3200 on bandwidth. Again, if you do not know what these values do, leave them alone at default. These are really good values to start with. And then with the prop pointing in the right direction, as you can see here on my rig, I'm actually going to go and take an initial run, and that will give me some parameters. Again, we can zoom in and out of our graph. This one is just basically just using the default low passes, and you can actually see the way this is this is working. It's actually giving us a good direction, but we want to use advanced filtering for this process. So the way that I will start is, having taken samples, I will bring on my FFT, and you can see right away that we have a couple of major imbalances according to our spectrum graph here. The first one is actually pretty high at around 165 at 50 Hertz, and there seems to be another one at 140 at 231 Hertz. Now this is probably like bearing, or it might be due to your setup with the rig. Net of it is there's two imbalances here, and what we need to do is isolate every single one of them and try to eliminate them. So the first thing that we do is this major one here, I'm more than certain is due to the prop, and using our advanced filtering we can actually go on ahead and isolate that. So the way that I do that is, if you click on the advanced filter tab here, you'll see that it brings up this window that allows you to choose between 3 different digital signal processing filters. Now these are pro level implementations, believe it or not, of these filters. I did a lot of work with the software. The Chebyshev filter allows an additional parameter for stop band ripple. Now I can have an hour's worth of a video here explaining the differences between the different filter types. Each one has pluses and minuses. I think for digital signal processing, these are the best 3 top best filters that you can use. And as you can see here, these are bandpass filters, which basically allow us to isolate a particular frequency. So again, knowing that the component we want to isolate is around 50 Hertz, what we can simply do is we can go here, and as you can see by defaults, we can leave it at that, because between a lower cutoff of 10 and an upper cutoff of 70, that includes the 50 Hertz component. And the fact that I bought this filtering window up places the entire software into digital signal processing mode, and you'll see the differences. It basically will collect samples when we do a run, and then once we have collected those samples, it will then proceed to run them through the filter. But then you can see once we have those samples that we can actually just continue to keep reusing them, so that we can continue to improve on our filtering. So again, orienting the propeller the way that I have it, I'm going to go on ahead with these parameters and take a run, same as before. Now the differences that you'll see is that there's no vector. You'll see that there's a lot of noise in the accelerometer because we completely disable any other filtering, and then you'll see when this is over, it will get processed by the DSP, and there you go. So what happened, and we can see some major differences here, including if we zoom out. Now you can see the functionality of the graph, that here's what the signal, the raw signal coming out of the accelerometer was, and after DSP was applied, here's what comes out. So it should be completely apparent that, you know, the way this bandpass filter is working is absolutely spot on, right, in terms of isolating that imbalance. Now what I can do is I created this refilter button here that once you click it, it basically takes all the samples that we collect them and runs it through the DSP again, so that if we make changes here, we can see what those changes are without having to take another run. In addition to that is if we bring up our FFT now, take a look at this FFT now. Before, you see that we had a lot of noise and we had some imbalances, but we completely have isolated our 50 Hertz component. So now we are laser focused right on that component that we want to eliminate. Okay, so not only are we identifying that we have this vibration, but now our rig is also capable of telling us where the imbalance is. And this is where the calibration part comes in, right? So again, if I take my prop, and I had it in this direction when I ran it, and I narrow my filter bandwidth down, let's say I'll go to 40, again the imbalance was around 50, and we run the calibration, look at the effect that that had in our imbalance vector. It changed it almost 90 degrees by completely refocusing on that 50 Hertz imbalance. And since we know that according to the way our setup is here, we had the reference blade here, the imbalance because of the tape was on this blade here, right, which is going to point to this blade here, we can manipulate our filter further to point in that vector. So what I do is maybe narrow it a little more. Okay, that had a good effect. Let me see the effect I'm going to have if I open it up in case there are any harmonics at the upper end. Okay, so that's good. Let me narrow it down a little bit more. Okay, so I'm happy with that result. Obviously, I'm going to need to now flip the blade, see if I get the same result at the other hand, on the other side. Maybe come in here and modify the parameters a little more. And then after I do that, I will then take this tape out and also make sure that I place weights on the bell here and there to align it as well. And there is also where you might want to use one of the invert buttons to get it aligned to your orientation. But anyway, let's see. We ran it this way. I'm now going to flip the blade. I'm going to have the heavy blade toward me, making pretend that's a reference blade, which basically should point the vector in this direction after all filtering is done. So let me go on ahead and take that run. It's going to be the initial process, very noisy. It's just collecting data, and after the data has been collected, it will then pass it through the advanced DSP for the data we really want, that 50 Hertz imbalance. Okay, look at that. Pretty much spot on. You know, we flipped the vector. It completely isolated the imbalance. And again, we can rerun it. Completely isolated the imbalance to that 50 Hertz component. Look at how clean our FFT is. and it pointed that, hey, your imbalance is on this blade, which is really what we wanted. Now you can go and fiddle with this to make it a little better. Again, let me see what the effect is of maybe not narrowing it as much. Okay, wrong way. I don't know. There you go. I'll open it up even a little more. You know, you play with these parameters. You know, for me, this is as accurate will get, right? I mean, it's right on the blade. It showed you where the imbalance is. The waveform here is absolutely, you know, stunningly clean and clear. You know, we can, I mean, this is almost a perfect sine wave. So you can really begin to see the effects of a good designed DSP filter is. And then again, you know, the only way that you can play with this is choosing different filter types. You know, it could be certain imbalances with your rig. You know, some filters are more linear, others are better at maintaining constant phase, others are better at having a sharper cutoff. Like for example on the Butterworth filter here, that's the case. And you know, just do some research on Google, and you'll see what are the differences between these filters. But what I wanted to highlight is how we were able to identify a initial imbalance and then completely isolate the imbalance so we can work on it. All right. So now if we know that this is our heavy blade, and we know, for example, that our rig is oriented correctly, that here it will point in the right direction, here it will point in the other direction, we can actually begin to balance the blade. I'll tell you what, let me take another run. I flipped the blade, the vector should point in the other direction to again confirm our orientation and calibration. You know, as you also can begin to see, an accelerometer with no filtering is pretty much useless. Okay, look at that. It is absolutely razor sharp, spot on, accurate. You know, by flipping the blade and our filtering, I mean, it automatically pointed with an extreme accuracy. I mean, with even 1 degree here at the 270 degree mark, which is exactly where we placed the tape. I'm just amazed, actually, by incorporating DSP filtering into the software, how much it has improved its accuracy. You could have gotten as close using low pass filters here, but you would have to use compensation, and that's absolutely possible. And the reason why I have left these parameters in here, it's because it's always good to be able to see almost like the raw state and play with some of these low pass filters as well to get you a decent result. Also, you know, we're balancing for 4-point, you know, for a 4-point balance, we do not need direction, right? All we need is force magnitude. So it's always good to leave the filters in here, because again, the more filtering we do, the more components we take away. For a 4-point balance, we want everything there, because all we're looking is for a magnitude, not a direction, right? So those will remain, but for balancing the blade, you can begin to see what improvement the filters make. Now, what I want to do here as a last item for this video is I'm going to actually go ahead and remove the piece of tape that made my propeller unbalanced. Okay, I have done some previous work to balance this prop. You can see some other pieces of tape on it, and you know what I want you to see here is, you know, this was what it was in an imbalanced state. You can see the magnitude of the filtered waveform. You can actually also see the magnitude of the total force. It was over 330 somewhat million, right? Again, this is just a number for us to use as a reference. Now, I know that this blade in this state is pretty well balanced, so I'm going to go ahead and take another run so I can show you the difference of what a balanced blade is actually going to look like. It's going to take the same samples. Now, the accelerometer graphs are going to be almost as big, because what we're doing is I've switched the accelerometer to full resolution mode, but the filtering, okay, should tell a big difference. And take a look at that, right? You can see the previous values were in excess of 200. Now with this, you know, we went from a 340 some odd million down to almost 34. All right, so this is what a decent balanced blade is going to look like. You can try to bring these numbers down. don't pay as much attention to the width of this because I have normalized it to about 16 million. So when this number begins to get below 16 million, you'll see this line get thinner and thinner, which basically means there's room for improvement, right? It shows us here that there's some sort of an unbalance in the hub, so you can add a few pieces of tape more to actually try and alleviate that, and we can keep refiltering, but we can also confirm this from the FFT. Our FFT was in the magnitudes of something like 140 or 50 or so, when we initially did this, and now look at the magnitude. It's just a little bit over 20. So we have done tremendous improvement in terms of balancing our prop, and you can clearly see that with your filtered graph, as well as with your FFT. Now, with that said, again, don't forget that what I did from a calibration standpoint is I placed a piece of tape on the blade, either here or there. But in order for you to do a complete calibration, you would have to remove the tape and then also place tape on the bell right here and there. Look at the previous calibration videos, because we really also need to take care of the vectors that might be pointing here and here before we can consider this completely calibrated for us then to go back and start to balance our prop. And then you might want to take a couple of runs. I'm going to take another one here. The readings might vary a little bit. There's, depending on how the accelerometer vibrates, you will have some variation. Okay, notice it was around 30, 33 or so. We went down to about 25. You will vary within maybe 10 or so million. But again, as you can, as long as it's not wider than that, also take a look at your graph here, and you can see that from a graphical standpoint, you have really done a lot of work in reducing those vibrations, which is a telltale sign that you are balancing your propeller a lot better. Okay, so I just wanted to introduce this. If you close down the bandpass filter window, that will automatically now put the program back into its normal mode, where you can use the low pass filtering, for doing runs. And then once you open up the filter window again, it puts it into DSP mode, and then varying your again your lower and upper cutoffs allows you to to tune it. So couple of other things to fix before this release is done, just making some additional improvements. So it would be relatively soon here, but I wanted to show you digital signal processing, because I think it has made a tremendous addition to the software in improving its accuracy, and certainly allowing you to to achieve an extremely well balanced setup, both from a motor perspective, but as well as a propeller perspective. Thank you for watching. Any questions, please post them in our forum and RC groups. Really would like to see a lot of your builds. Have a lot more folks using the software with different builds, so way we can work out any kinks. And really the only way that we're going to learn and keep improving it is by having those results. So thank you for watching. Let me know if you have any other questions. I'll see you on the forums.